Сейчас я проверю там у себя. Идет раз.
Good afternoon, everybody. Here we are. We start the lecture on medical and biological physics. It is the final lecture that completes this medical and biological physics course discipline you are learning now. A lecture is on ionizing radiation and this radiation implementations in medicine. The second question is the methods of protection and prevention of a human body. There are two questions, there are 2 points of this lecture will be considered. The first, the X radiation, and the next, radioactive decays radiations. Let's start from this X radiation production and implementation in medicine. X radiation is produced, is generated from the X-ray tube. It is the glass vacuated tube, including 2 theta electrodes. First electrode is connected to the negative pole of the external high voltage supply, and this electrode looks like filament that is coiled, and as you can see here, it is connected to the filament voltage supply as well. That is heating the filament. To be heated, this filament emits electrons, and these electrons emitted by the filament then are accelerated into the space between anode and cathode. Cathode is of disc shape and it is rotating. So, and what is the idea? To arrange the producing of the X radiation. The idea is to accelerate the electrons into the space between cathode filament and anode rotating disk, and then to stop electrons. As you may remember, electrons are electrically charged particles. They carry negative elementary electrical charge, and when they are stopped by this disk, behaves itself as the target bombarded by electrons. Just this is the procedure of the deceleration of the electrons, and energy, electrons kinetic energy, is transferred into electromagnetic energy in the only 1% of the number of the electrons, and 99% of the energy, kinetic energy of the electrons disappear as the heat. So this means that the target, the anode, the disk requires the cooling, and this is done by the conversion of the oil. The tube is placed into. So this is just the idea of the generation, and you can see how small is the efficiency of X-ray tube. The only 1%, or it might be less than 1%. So what is the spectrum of the electromagnetic energy radiated by the X-ray tube? There are two kinds of energy emitted from an X-ray tube, and this is displayed as the range of energies, and hence frequencies and wavelengths. The distribution of these energies is called the X-ray spectrum, which is usually represented as a function of photon energy, but can also be illustrated as a function of wavelengths. This is just the spectra of the X radiation. Continuous spectrum. A continuous range of the photon energies up to maximum is produced as electrons are decelerated in the target. What is actually energy that is emitted when electron strikes the target? As it was said already, it is the transformation of the kinetic energy of the electron into electromagnetic energy of X radiation. Thermo-ionic emission of the electron from the filament produces the electrons with different initial velocities. So the acceleration into the space between the filament and target in turn provides electrons with the different final kinetic energies. Consequently, when electrons with the different final kinetic energies are stopped by the target, they produce the different energetic photons of the X radiation. So this is the reason to produce this continuous spectrum, the different initial velocities of the electron that are removed from the filament by the thermo-ionic emission. Some of the electrons may be provided by acceleration of the great energy, and this energy may provide the penetration of the incoming electrons into target atoms, and incoming electrons strike the inner electron of the target atoms and remove that electron from their K shell, for example, and electrons from the target are ejected by that means. So this K shell energy is less than higher shell's energies. So consequently, the outer electrons go and fill this inner shell electron position, and the electron that fall in the K shell emits a photon of energy, and this develop the series of K lines. Also, the electron from the target atom may be removed from the L inner shell, and consequently the higher electrons from Mn shells fall in and produce the L lines. These L and K lines are determined by the material of the target. So that is why this line spectrum should be considered as characteristic spectrum representing the material of the target. A limited number of precise characteristic photon energies is generated through electron transitions to the K and L shells. These are two kinds of the X radiation spectra: continuous spectrum and line spectrum. These are because of different final kinetic energies of the accelerated electrons striking the target. When X radiation goes through the substance, goes through material, attenuation mechanisms of this radiation may be considered. What is actually attenuation? Attenuation, it is the decrease of the intensity of X radiation because of the interaction with the atoms of the materials substances. So, and these interactions, the characters of the interactions depend on the X radiation energy. Actually, we can see now about one more physics model that is useful now to consider the structure, the nature of X radiation. This radiation may be considered as the flow of the something looking like particles. What are these particles? These are not material particles, but instead these are located portions of the energies. And these portions of energies is named as quanta or photon. So, and you can see after we use this physics model of electromagnetic radiation as X radiation, it is very simple to describe how X radiation as electromagnetic energy is attenuated by the substances. Look here, when low energy X-ray photon meets the material substance atom, this energy is absorbed by atom, and atom goes, electrons into the atom, goes from the low energy states into the higher energy states. It is just the excitation of the atom. But this position, exciting position, to be excited, is not stable for the atom. And after a very short time, the atom falls, goes, returns to its original non-exciting state. And the photon is re-emitted by the atom. The energy, the rest of the energy atom obtains is released as the photon of the same energy as the falling X-ray photon. But you can see here at this diagram the direction of the motion of the re-emitted photon is different with respect to the falling, striking photon. So that is why this is the simple scatter. What is the scattering? It is the change of the propagation of the radiation independently on its wavelengths, independently on its energy. The incident photon energy is much less than the energy required to remove an electron from its atom, the binding energy. The photon is simply deflected without change of energy. It is scattered elastically. The photon gives up all of its energy to an inner orbital electron, and when this photon energy is slightly greater than binding energy, this follows with ejecting electron from its atom. Excited atom subsequently returns to its ground state with the emission of the characteristic photons, most of which are of relatively low energy, and immediately absorbed in the material itself. This is just photoelectric effect. The photoelectron, the inner electron that is ejected, is developed, and low energy photon emitted to be characteristic of target atom of the material. The ejected photoelectron ionizes further atoms along its path until its kinetic energy has been dissipated. So this photoelectric effect, the attenuation mechanism for the X radiation of photon energy that is slightly greater than binding energy of the electron into the atoms of the material that the X radiation crosses. The third attenuation mechanism is the Compton scatter. If the energy, it will happen when the energy of X radiation photon is much greater than binding energy of the electrons into the material atoms. If it is so, the only part of the photon energy is given up during the interaction with an outer valence electron, which is effectively free. The photon then continues in a different direction with diminished energy, and the electron that is named as recoil electron dissipates its energy through ionization. So this Compton scatter, one more time, the low photon is produced by the material atoms, but these are of different direction of the propagation, and recoil electron is produced as a removed electron, outer electron from the material atoms. In all three cases, you can see what happens when X radiation crosses the material. Atoms are excited, electrons can be removed from the atoms, and These, when we take in account that this may happen into the human body tissues, you can see that it might be hazard for the organism. Different attenuation mechanisms dominate at different photon energies. This was mentioned already, and you can see simple scatter is dominant for the energy X radiation photon of that range. Photoelectric effect requires more energy, and Compton scatter is caused by the photons of that range of the X radiation photons. And from here you can see one more thing, the dependence on the material, that or another mechanism. And the photoelectric effect at the greatest extent depends on the type, kind of the material. Z, it is the number of the element crossed by X radiation. Different attenuation mechanisms dominate at different photon energies, and you can see that this photon energy of 30 kilo-electron volt is chosen to provide the most contrast image of the tissues when internal structures of the human body are under investigation. An image intensifying screen with double-side film placed to receive X radiation direct from the patient and light from both the screens. In practice, this can intensify the image by up to 40 times. The resolution of direct exposure film is about 0.1 millimeter. This can fall to 1 millimeter with fluoroscopic screens. This is used for still photography to produce radiographs. The use of the intensified tube overcomes the need for a greater intensity of X-rays by coupling the fluorescent screen to a photocathode and electron gun. The electrons emitted by the photocathode are accelerated onto a second fluorescent screen containing zinc sulfide. The energy they have gained, intensifying the original image, usually by a factor of up to 1000. The signal can then be fed to a video camera for real-time viewing using a television monitor or video recording. You can see these radiographs of normal knee displaying smooth surfaces and abnormal surface of the knee. You can see the irregular bone surfaces and evidence of increased bone growth. So this is just the evidence of the abnormality into this structure that is evidenced. The X-ray of the lungs of a tubercular patient shows patchy areas where the disease has damaged the lungs. Tomography is one more technique that demonstrate implementation of X radiation for medical purposes. This is a technique for producing an image of a slice of the object. At its simplest, it is a way of arranging to have one plane produce a clear image, regions above and below being blurred. Since X-rays can't be focused by lenses, this is arranged by moving the X-ray tube and the film cassette. The two are connected mechanically so that as they move, the image of the chosen plane stays in the same place of the film. The image A stays as a prime object. That are not in this plane, such as B, are imaged in different positions as the unit moves from B prime to B2 primes. X-ray therapy requires much more energetic X-radiation photons, and you can see the kinds of the therapy and typical photon energies that are required for that kinds of the treatments. And you can see the voltage range for acceleration of the electrons. And now let's consider one more, ionizing radiation. This radiation of three kinds, and it is accompanying the non-stable nuclei decays, unstable nuclei decays. First of all, several words, the short review of the nucleus structure. Nuclei, it is the subject for the objects for the study of the nuclear physics. That is the field of physics that studies the constituents, protons and neutrons, and interactions of atomic nuclei. The atom, you know, consists of a small but massive nucleus surrounded by a cloud of rapidly moving electrons. The nucleus is composed of protons and neutrons. Total number of the protons in the nucleus is called the atomic number of the atom and is given by symbol Z. The total electrical charge of the nucleus is therefore the atomic number times elementary charge magnitude. In a neutral atom, there are as many electrons as protons moving about nucleus. The number of the protons in a nucleus and electrons in the atom, if the atom is not ionized, is represented by Z. The number of the neutrons may be calculated as the difference between the mass and charge number or charge number of the atom. Neutrons and protons are called nucleons. So A is the number of the nucleons in a nucleus. We identify nuclides by writing the symbol of the element. For example, the most abundant isotope of the iron has 26 protons and electrons and a mass number of 56. So this element, this isotope of the iron may be represented symbolically by that means. Atom number, atomic mass number, and the number of the protons and electrons. When we say about the proton, these are positively charged particles, and it is might be surprising from electricity point of view that these same sign charges are kept together within the nucleus, and huge energy is required to separate these positively charged particles, remove them from the nucleus. Now, why is it so? Because of the nuclear force, properties of the nuclear force that keeps together the neutral, electrically neutral particles, neutrons, and positively charged particles, protons, are these. Nuclear forces are attractive in nature. Nuclear forces are independent on electrical charges, signs. The range of nuclear forces is short, and the nuclear force is dependent on the spin. When we calculate the free nucleons mass, sum of the nucleus mass, and compare with the nucleus mass, we can find that is named the mass defect. The nucleus mass is always less than the sum of the masses of its separate protons and neutrons. So, and it is the question, where has the mass gone? It has become energy, such as radiation or kinetic energy released during the formation of the nucleus. This energy is known as the binding energy of the nucleus. It is some of the presentation may be suggested. Look, when the protons that are positively charged particles start to develop the nucleus, they are under a nuclear force, and this force is attractive force, and this force, nuclear force, as any force, accelerate particles, protons particularly, to keep them together to develop the nucleus. And we know that charged particle starts to be accelerated. It generates, it radiates the electromagnetic energy, electromagnetic waves. We considered this already. So consequently, when protons and neutrons develop nucleus, they release energy into the space in form of electromagnetic energy, and by that means they lose energy. And to separate them, this energy that is named binding nucleus energy is required. So, and this relation between the defect of mass and the energy lost may be supported by this formula, that Einstein formula, revealing the relation between the energy and mass. So the nuclear binding energy is calculated per one nucleon. Nuclear binding energy per nucleon is defined as the average energy per nucleon needed to separate a nucleus into its individual constituents. It is denoted by that symbol. If we plot the graph of the binding energy per nucleus, per nucleon, and the mass number, we obtain such a line showing the range of the elements that are of greatest stability. What does this mean? This means that the energy to separate that nuclei is required the greatest with respect to other elements from left and from right of this region of greatest stability. The nuclear binding energy per nucleon, the characteristic, the measure of the stability of the atom's nuclei. When the ratio of proton to neutrons falls, when the ratio of numbers, it will be more correct to say, of proton to neutrons falls outside a certain range, the nuclide is unstable. It decays to another nuclide with the emission of radiation. Three types of radiation are emitted spontaneously from the nuclei of certain atoms. Gamma radiation is similar to X radiation. It is the electromagnetic radiation. Beta and alpha radiations are substantially different in their nature and in the way they interact with matter. Radioactivity, radioactive decays, occurs due to the decay of the nucleus. External parameters such as temperature and pressure don't affect the rate of decay. Radioactivity is based on the law of conservation of charge. The daughter nuclei will have unique physical and chemical properties. It is absolutely different nuclei that is different from the parent nuclei. The decay rate of any radioactive material is directly proportional to the number of atoms present at that instant. Alpha, beta, and gamma rays are followed during the radioactivity. Actually, the radioactivity should be defined as the ability of the nuclei of some atoms to decay, and the decays are accompanied by these three kinds of the radiation. So here you can see how the radioactive decay law can be derived. What is the idea of that law? To show the change of the number of the radioactive element nuclei with time. And this radioactive decay law states that probability per unit time that a nucleus will decay is a constant. Probability per unit time that a nucleus will decay is a constant, independent on time. So that is why the radioactivity, it is the intrinsic property of the nuclei of that are not stable. The probability is represented by the decay constant. And final equation, analytical equation that represents the law of radioactive decay is this one, showing how many of radioactive nuclei are left not to be broken down out of decay after this time of observation. And this n with index 0, it is the initial number of radioactive nuclei. And lambda is the decay constant. It is the measure of the ability, of the strength, it might be said, of the ability, the strength of the ability of the nuclei to decay. One more characteristic of the nuclear decay may be suggested. It is the rate of the decay. How much decays will take place per unit of time. So, and the rate of decay is represented by that means as the change, the number of the decays, the change of the number of the radioactive nuclei within this period of time. When we divide this change of the radioactive nuclei over the time of their decays, we obtain the rate of decay. And the change of the rate of the decay with time may be represented by this analytical formula. The total decay rate of a radioactive sample is called the activity of that sample, which is represented with the unit becquerel. So it is the rate of decay, and it is the one more name for this. It is the activity of the sample. And let's review the kinds of the radioactive decays. Radiations. Decay by alpha particle emission occurs mainly amongst nuclei of the heavier elements of atomic number greater than that of the lead, Z equals 82, and results in a reduction of 2 in atomic number, Z, and 4 in mass number A of the radionuclide. You can see that the alpha particle actually it is a helium nucleus. It is the helium nucleus. So, and these are examples of the alpha particle emission decays. You can see these are very heavy nucleus as well as these and these. Alpha particle emission takes place removing 2 protons and 2 neutrons. And this new daughter nucleus becomes less heavy. A beta particle can either carry a negative charge of the familiar electron or equal but opposite positive charge of the positron. In beta electron decay, a neutron transforms to a proton. In beta positron decay, a proton transforms to a neutron. And these are the reactions of beta electron and beta positron decays. Gamma rays are high energy electromagnetic radiation, and we can say that this radiation is accompanying beta or alpha emissions. Often follows another decay processes. Poor gamma emission alone doesn't change the A or Z numbers of the nuclide. Gamma rays are high-energy photons produced in association with other forms of decay. Gamma rays are massless and don't, by themselves, change the nucleus. Let's look inside the material that is crossed by nuclear decay radiations. The overall process of interaction of nuclear radiations with tissue, particularly with tissue, is very similar to that described for X-rays. The absorption of energy causes ionization and excitation, which results in chemical changes with a range of biological effects. To describe the more detailed the penetration of the tissue by this kind of nuclear decays radiations, the number of pairs of ions produced per millimeter of air is taken. Look, and you can see how many pairs of ions is developed, is produced by alpha particle. It is a very heavy particle with respect to beta particle, for example, and so striking the atoms of the material it is crossing the alpha particle produces such many pairs of ions, 1000 into 1 millimeter of the air layer, and 100 times less number of ions pairs are produced by the beta particles. So the penetration of the beta particle is 100 times greater than that of the alpha particle. And you can see how small the only one pair of the ions, positive and negative, is produced within the 1 millimeter layer of the air by gamma radiation. So this is just the most penetrating radiation. When radiation passes through something, its energy is absorbed there, and we can say about the energy that is absorbed by the unit of mass of the material. And this becomes to be measure of the radiation. It is the absorbed dose. The next characteristic may be taken as the measure of the radiation. It is the development of the electrical charge of one sign into the material. We deal actually with the ionizing radiation. So, and it is reasonable to measure radiation amount by one more dose. It is the exposure. Exposure, it is the amount, the magnitude of the charge that is developed within unit of the mass of the material. These two, absorbed dose and exposure, are basic measures of the intensity of the radiation, meaning the effects provided by the radiation. But doses, weighting, health effects of respective types of radiation are equivalent dose. The effective dose was developed for exposure management in radiological protection. In contrast to the equivalent dose, the effective dose weights differences in sensitivity among organs and tissues and sum them up to express the radiation effects on the whole body. So this is just the concept map of the doses as measures of the effects, influence on the human tissue, on the human organism. Absorbed dose, amount of energy absorbed by substance of unit mass that received radiation. This is the formula to calculate absorbed dose. But this doesn't say what it will be the effect. Would it be harmful? Would it be hazard? So that is why we should go further. Differences in effect depending on types of radiation. And this is measured by the equivalent dose. But one more time, it is not the direct information about particularly harmful effect of the human tissue or hazard of the human body. So that is why we should take in account the difference in sensitivity among organs. And this gives effective dose. And finally, how this effective dose is calculated. It is radiation weighting factor. It is the equivalent gives the equivalent dose. And shows the differences in effect dependent on types of radiation. Then the tissue weighting factor should be involved. And what it is? It is the differences in sensitivity among organs. And finally, the effective dose, just that showing the resultant effect on the human body is determined as the sum of these all effective doses of all kinds of the radiations. These are measures, doses of ionizing radiation. And look, it is stated that alpha particles have 20 times larger effects on the human body than gamma rays and beta particles with the same absorbed dose. Neutrons are also given high radiation weighting factors and are expected to have from 2.5 up to 21 times larger effect on the human body. Gamma rays and beta particles depending on the energy quantities. And you can see equivalent dose, radiation weighting factor, type of radiation, and times absorbed dose, effective dose. This is the sum tissue weighting factor times equivalent dose. And by that means this effective dose is obtained, and the conclusion about the effect on the human body is made. How radiations may be recognized, meaning the presence of that radiations. Radiation is known to interact with the substances when passing through them, and this is the base to recognize, to determine their presence. Ionization is one major of the interactions with the substance of radiation. Detectors are filled with gases such as inert gases or air, And you can see this gas is fills the space between two electrodes, cathode and anode. When radiation passes through gas, molecules are ionized, creating positive ions and electrons. Positive ions and electrons are drawn toward electrodes and are converted into electric signals, and this signal electrical current is measured. It is the idea to recognize the presence, to detect the ionizing radiation. What else may be suggested? Excitation. When radiation passes through a scintillator, molecules are excited, but they return to their original state, ground state, and this coming back is accompanied by light emission. This light is amplified and converted into a current for measurement. So this is the one more idea to detect ionizing radiation. And this as a Geiger counter is one more that is widely spread to detect ionizing radiation, to recognize the presence of that radiation into the surrounding, into the space. The counter contain tube, the element of sense that detects the radiation, and electronics that process, that provide the result. The counter tube is filled with a gas such as helium, neon, or argon at the pressure being the lowest where there is an application of high voltage. It is just the idea of the ionization is released here. There would be the condition of the electrical charge on the tube when a particle or photon is of incident radiation would turn the gas conductive by the means of ionization. And this reading shows not only the presence but also this electronics provides the measurement of the intensity of the radiation. The larger current, the more intense radiation present into the surrounding. And several words about ionizing radiation cause that process into the tissues. Ionizing radiation may cause much more severe damage by breaking bonds or removing electrons in biological molecules, disrupting their structures and functions. The damage can also be done indirectly by the first ionizing water that is most abundant molecules in living organism. Look what may happen because of that indirect effect of X radiation, the radiolysis of the water. But before we consider this, let's consider the phases. That is physics and chemical phase of the effect of radiation, the substance. On the substance, radiation crosses. Look here, the photon of ionizing radiation of less than binding energy of the atoms of the substance is absorbed by the atoms of the substance, and this excites the atoms and returning to original state, atoms of the substance radiated by that or another kind of radiation returns to its original ground state and emits the photons, and part of the energy is released as the heat into the substance. So if energy of the radiation photon is greater than binding energy of the atoms, of the electrons into the atoms of the material, this as photoelectric effect will happen. It is just ionization. And this Compton scatter the photon energy is great enough to ionize molecules or atoms of the substance, and some of the energy goes free as the second scattered non-elastically photon. And after this, let's consider these physics and chemical combination processes. The ion, in some cases, after ionization, is not stable and spontaneously breaks down into two fragments. So, and excited atom may be may obtain the ability to interact with the atom or other molecule that is not allowed without this atom excitation. This excited atom becomes more active and may interact and to produce the new substance that is not normal for that material, that is not present before radiation incoming into the material. And look, this happening with the water molecules. You can see that ions and radicals are developed, and this leads into the chemical stage to the production of these dangerous substances that can destroy the cells and structures of the tissues. Radiolysis of the water. And let's complete the nuclear physics option by the review of some technique implemented in medicine. The static imaging that is obtained by gamma camera. A modern compact gamma camera is at the heart of this whole body scanner used for detecting the spread of cancer through the body. What is the idea? The idea is to insert to inject into the bloodstream through the vein the radioactive metastable element and to detect the gamma radiation going from the patient. And the abnormal regions store the element at greater extent than normal structures. It is the specificity of, for example, cancer tumor cells. So, from that regions, the radiation, gamma radiation, will be more intense, and this more intense radiation will reveal that abnormal regions, that abnormal structures. And this is the block diagram of the gamma camera. The gamma camera had this is the patient. The gamma rays go from the body, and after that this gamma rays electromagnetic radiation is detected and processed. Light photons from the scintillator fall on the light-sensitive photocathode of the photomultiplier tube, thereby ejecting photoelectrons. By the photoelectric effect, the photoelectrons are then accelerated toward the first of the series of electrodes. These are diodes that are held at increasing positive potentials along the tube. Each electron incident on its surface easily ejects from a few secondary electrons. These in turn are accelerated to the next diode, where further secondary electrons are ejected, and so on down the chain of normally 10 diodes until the final anode is reached. If there is an average multiplication of 4 at each of the 10 diodes, every primary photoelectron will result in a pulse of 4 to the power 10 secondary electrons at the anode. Such a large overall gain enables even low energy radiations to be detected and measured. So, an important feature of the PMT is that the size of the output electrical pulse is directly proportional to the incoming visible photon energy, since each pulse of light is amplified by the same factor. For example, if 4 visible photons fall on the photocathode, the output pulse will be 4 times as large as that due to 1 visible photon arriving. This provides a means of identifying where in the patient the original X-ray originated, since the largest signal will come from the PMT closest to the scintillator, which in turn is in line with the source of the the gamma ray. An array of up to 75 PMTs is located behind a single sodium iodine crystal, and from the output pulses, electronic analysis can easily identify the location of the incoming gamma ray. The associated circuitry, the position, decoding circuit compares all the PMT pulse values and ascribe an XY location of the incoming gamma ray. This, however, is not enough. We need to establish that the incoming gamma ray actually came from the scanned radioisotope and not from some other source or from heavily scattered lower energy radiation. To do this, it is the role of the associated circuitry. And you can see not static but dynamic kidney study using this radionuclide as metastable technetium. It is inserted intaken by the patient. The blood flow delivers the structure with this radioactive nuclide. It emits the gamma radiation, and this radiation that is changing with time is detected and shows the process in progress at kidney, for example, that is pair organ. There is an obstruction to the outflow of urine from the patient's right kidney. It is shown here directly. You can see the retarded function of the right kidney from both the images and graphs. If untreated, this condition often leads to kidney failure. And here, finally, look at this table where you can see the radionuclides list that are used in medical imaging. The idea is the only one to inject, to intake that or another nuclide, and to register, to indicate, detect the gamma radiation from inside of the body, and recognize how these intaken radionuclide spread into the structures, and compare that regions, meaning the measurement of the intensity of the gamma radiation. You can see what are these and what are the investigations listed here that are under interest, that are under study of the doctors. So then we finish. Thank everybody for attention.